I do. There's no danger, no need to change that front.
Might as well start. Yeah. We're all here. Yes. Okay, right. Welcome, everyone. So today's colloquium, we have Joanna Fawcett from Imperial College London, and she's going to talk about homogeneity in graphs.
Thank you, Michael, and thank you to the organisers for inviting me to speak and for inviting me to this program. It's been really, really lovely. So today we're going to be looking at graphs with lots of symmetry, and I'm just going to put some restrictions on the graphs I'm talking about today. They will be finite. They will all be simple, so no multiple edges or loops, and they will be undirected. Basically, everything I'm going to say today there's plenty of things you can say for all of these, but I'll be here all day if I try to talk about everything, and it tends to be easier to write things down when things are finite. Okay, so the whole talk centers around this definition. So let's let X be class of graphs. And say graph gamma is X homogeneous if the following condition holds. So for any graph isomorphism phi between delta 1 and delta 2, it's a bit of a mouthful, for induced subgraphs delta I of gamma. Yeah. Where delta 1 is in my set X. I'm being a bit lazy here, and E is isomorphic to something next. So for any one of these, there exists an automorphism of gamma extending the isomorphism Y. So what's an induced subgraph is take a set of vertices and take all, you say an edge is in the induced subgraph if and only if it's in the graph.
So phi is supposed to be an isomorphism, is it?
Yes. Oh, I didn't write it. Make sure. That's rather critical. Thank you. So any isomorphism we can extend. So what I'm going to do, because I'm going to be talking about a lot of different possibilities for X, and I think everybody will get completely lost in all the names. So I'm going to create a giant table, which will get updated throughout the talk, which also means that I don't have to use this board very much. So this will be a big table. So I've got X, and I've got X homogeneous. So what can we say? Well, the most basic thing you could do would be, well, let's take X just to consist of a complete graph, just one vertex, no edges, of course. Well, here, being X homogeneous is just the same thing as being vertex-transitive. That's not particularly interesting, but it's good to note. So if I keep going, if I take K2, so an arc, well, it's just arc transitivity. So I can take any ordered pair of adjacent vertices to any other. Okay. Another option would be to take all graphs. And this is normally referred to as homogeneous, which is where the term X-homogeneous comes from. But this definition comes with a health warning. In the literature, sometimes this is called ultra-homogeneous, and homogeneous is reserved for a weaker condition, so be very careful. When looking at the literature. I think it's about 50-50. So this is my choice. Okay, so let's see some examples. Alright. So first example, nice and tiny. The cyclic graph C5. Just 5 vertices in a cycle. So what do the induced subgraphs look like? Well, think about the connected ones first. I mean, obviously you could take the whole graph, but that's pretty boring. So take a proper one, it can only be a path, right? It's the only kind of connected induced subgraph I can have. And if I take any two paths with the same number of vertices, I can take one to the other, because I can just rotate until they occupy the same set of vertices, and then I can reflect if necessary. And so all connected induced subgraphs work. What about disconnected ones? Well, I could take the graph, usually called 2K1, so 2 copies of the complete graph in one vertex, or just 2 things that are adjacent. And actually, there's only one other one, which is just something that looks like that. So what about those? Well, actually, I can be a bit cheeky here, because if you notice, the complement of this is an arc, and the complement of this is a path with 3 vertices. And this graph is self-complementary. If you think about it, if a graph is delta homogeneous, where delta is a graph, then the complement is the complement of delta homogeneous. Because if you take any set of vertices, if it induces one graph in the graph, then it will induce its complement in the complement. Right? So, and the automorphism groups are the same. So actually, I can be kind of lazy and just say I need to find them. So this is an example of a homogeneous graph. Okay. What about C6? Now I've got 6 vertices. So let's look at the connected ones first. Well, by exactly the same argument I gave before, they're all fine. Nothing changes. And then I look at the disconnected ones. So the smallest one will be this guy. Again, but I've got a problem. So if I take, say, those 2 vertices, that gives me one of these subgraphs. And if I instead take, I'll put squares around them, those 2, I would have to be able to fix this vertex and map that one to that one, but I can't, because these 2 are at distance 2 and these 2 are at distance 3. Right, so this is not homogeneous, but all connected graphs work, so that's quite nice. And so we usually give this a name, connected homogeneity, so I can add that to my list. Connected graphs. So call this property connected homogeneity, but it's so long I'm not even going to write it down once. I'm just going to abbreviate it to CH. And actually, you get exactly the same observations for any cycle. For at least 6. It would be CH, and it would fail for this graph. Okay, one more example. So if I take n copies of the complete graph with n vertices, so I've just got all possible edges, and so on. So I've got m copies of those. Well, what are, so no edges in between the blocks. So what are the connected and induced subgraphs here? Well, there aren't really that many of them in some sense. They're all unions of cliques. Right, I'll just have a clique here where everything's adjacent and maybe one here, maybe, you know. So a clique is just everything's, no, I thought you said connected.
I thought you said connected.
Oh, did I? Yeah. So, okay. Sorry. So what's the automorphism group of this graph? Well, it's the wreath product of the symmetric group Sn acting here and then with the symmetric group Sm. And so this is going to be homogeneous because I can move these around as necessary to line up my cliques with the same numbers, and then I can do whatever I want in here to move them around. And so this is another example of a homogeneous graph. And by what I said earlier, that means its complement is also homogeneous. So, complement of this graph, which is just the complete multi-part type graph with m parts of size n, is also homogeneous. We've got some nice big infinite families there. Okay. So, what are some basic properties? This X-homogeneity business. Well, the first one I've already said and used a couple of times. So, delta is a graph. Then gamma being delta homogeneous implies that the complement gamma bar is delta bar homogeneous. So we've already seen that that's quite a handy observation. Another one would be, so if I take this graph, so 2k1, and 2k1 homogeneous, then such a graph is either a union of complete graphs, so this graph there, or it's connected with diameter 2. So this tiny little graph has huge control on the connected structure and the structure of the connected components of the graph. So why is this? Just briefly. Well, if it is connected and it has diameter at least 3, we've already seen the argument which shows that that's no good, right? So if it's connected, it's diameter at most 2, and if it's diameter 1, then it's just a complete graph. Fine. So what if it's disconnected? So then I have at least 2 connected components. Let's suppose that one of them isn't complete. So I've got some non-adjacent vertices in that one, and I've got some vertex over here. To be 2k1 homogeneous, I have to be able to fix that one and send that one to that one. But if I fix that one, I have to fix the whole connected component. So there's no way I can send that one to that one. So actually that tells me that all the connected components have to be complete, and then you can just swap vertices as necessary to check that they all have the same size. Great. Okay. So if instead X is a class of only connected graphs, and to make things easy, let's put the one vertex graph in there. Then graph gamma is X homogeneous if and only if gamma is isomorphic to a bunch of copies of the graph sigma, where sigma is a connected X homogeneous. X-homogeneous, then if you look at the connected components, this ensures that they'll all be isomorphic. So I've got this for some graph sigma. And then if I take any induced subgraphs of sigma, there will be some automorphism of the whole graph, which takes one to the other. But it must fix that connected component, and therefore you get an automorphism of sigma. And going back, the fact that sigma is connected because everything in X is connected, everything in X is connected means whatever induced subgraphs we have of this graph must sit inside of sigma. And so it's not hard to see, you can go back. The automorphism group of this will at least contain the automorphism group of sigma in a reproduct of S. So this kind of, one of the first things you would think about is connectivity with this kind of problem, and this gives you a sort of idea of the dichotomy that can happen. But generally speaking, one cares about connected graphs in either case. Okay, so I want to spend a little time answering the following question. Well, actually, the rest of the talk, but so what is a good choice for the class X? And for today's purposes, I'm definitely not advocating you should always take this to be your definition of good. But just for today, good equals can classify. Okay. So a good illustration of this would be vertex-transitive graphs. These are lovely. We spend a lot of time studying them. So I'm certainly not saying that they're bad, but by my definition of good today, they're not good. So it's a sad face. We'll never be able to list all the vertex-transitive graphs, and similarly for the arc-transitive ones. This is also sad. What about all graphs? Well, if we can't do this, I'd say we're stopped. So I'm happy to report that this is good. There's a theorem due to Gardner, 76, and also independently Goldband, 78. The finite homogeneous graphs are, well, we've already seen a bunch. We've seen these two families here. So MKN, complete multipartite graph KMN, for sensible M and N, C5. And it turns out it's only one more. So, very expensive writing this graph, but Cartesian product of K3 which itself, what is that? It's just you arrange your 9 vertices in a grid and join things if they're in the same row or the same column. So, I mean, you would have found this example pretty quickly once you've seen 2. And so really, this is saying that homogeneity is an extremely strong property. 2 obvious examples, 2 more graphs, and that's it. So this gives you some idea of why we might consider X-homogeneity in general. Okay, so what about connected graphs? Well, this is also good. Smiley face. So this is also due to Gardner a couple of years later. 78. So he proved that CH connected homogeneous graphs but I won't rewrite those. And we've already seen that all the n cycles are examples. And you get the rest of these defined similarly. So Cartesian product of complete graph of itself. And then you get a direct product of K2 with Kn, which is basically you take a bipartite graph with two parts of size n and then remove the complete matching. Another way of defining it. And then we get the Peterson graph, which has to pop up somewhere. It does here. And then one more graph, the folded phi cube. Doesn't matter if you don't know what that is. Some people call this the cleft graph. Some people call this the complement of the cleft graph. So I'm going to call it the folded phi cube. Right. Okay, so that's good. We know the CH graphs. So that you might be thinking, well, I mean, these are awfully big. You know, can we do better? Well, what if we only care about graphs up to some certain order? So it's quite a sensible thing to consider. So graphs with at most k vertices. K homogeneous in the literature. It also comes with a health warning because this has nothing to do with the concept of K homogeneity with permutation groups. So don't get confused. So Peter proved in 1980 that 5 homogeneous implies homogeneous. That's quite a striking result. So you only actually need graphs with at most 5 vertices to get homogeneity as well. This is proved without the CFSG, so making it even more remarkable. So this gets a smiley face, at least for k equals 5. K equals 1 is just vertex-transitivity, so it won't for that. I'll come back to smaller k a little bit later. But another sensible thing to do would be, okay, well, this works for homogeneous, so can we do the same thing with connected homogeneous? Connect graphs with vertices. All this shockingly KCH. So I got that. So proved with Alice, Cheryl, and Jinjing. That, oh, I forgot to give you a definition. Where should I put it? Oh, I can put it right here. So, definition. So I have a graph. A local graph. Here's the graph induced by a neighborhood of a vertex, so all the things adjacent to some vertex, which in something like a vertex-transitive graph, they're all isomorphic, so this makes sense. And so you can say a graph is locally y if y is some graph or property which the local graph has. So here we proved that if you're for CH graph is connected, then it's either homogeneous or two exceptional graphs. So one is the Schlafly graph, if you know what that is, and the other is the McLaughlin graph, which is the graph you get from the rank reaction of that sporadic simple group. So actually, this is still quite strong. In general, we don't have a complete result, so I should update my list into sort of a kind of average base. It's for k at least 4. It's basically hopeless in full generality for k smaller than 3, but for k at least 4, it's okay. There's hope. So we proved that, so a 7CH locally disconnected graph with group 3, which just means it has 3 cycles, induced 3 cycles in the graph, and no induced C4, no induced quadrangles, implies it's connected to homogeneous. So there's this bit of nonsense here, which is why I can't put a happy face. We don't know what happens there. So I don't want to talk about this now, but this might be something to come back to in the future. But anyway, we can say quite a lot in that case. Okay, so what are some other possibilities? Well, everybody likes complete graphs, and you know, we couldn't do these ones, but what if we took all complete graphs? Is that a good choice for X? Well, the answer is unfortunately no, because we can't classify the arc-transitive graphs with girth bigger than 3, with no triangles. And any such graph will have this property, because the biggest size induced subgraph it has is just an arc. It doesn't have any triangles. So, under my extremely strong definition for what good means, this is not good. And so by this property, is it still there? Property 1, it tells me that also the edgeless graphs are no good. I'm not even going to give them a name, because they're so bad. But I find this really interesting. If you take the smallest bits of both of these, then we're in a completely different situation. So if I take a graph with 1 vertex, a graph with 2 adjacent vertices, and a graph with 2 non-adjacent vertices, so in other words, this is exactly the 2 homogeneous graphs, by my definition up here, then this is a good choice. In fact, this is a great choice because I've just explained that you can't remove anything from that set. So this gets a big smiley face. So I'm just going to take, oops, what does that mean? So I'm just going to take a couple minutes to explain how this works. Right, so the definition which many people in this room will be familiar with. So let's just take a subgroup symmetric group that's transitive. So an orbital of G is an orbit of G on omega cross omega, and rank of G is the number of orbitals, and so if O is a non-trivial, which by that I mean not the diagonal, self-paired orbital, so by this I mean symmetric as a relation, then O defines a graph. Just take two vertices to be adjacent, whatever they're in the orbital O, whatever the pair is in the orbital O, graph gamma, with G sitting inside the automorphism group of gamma, and this will be arc transitive, so G is acting arc transitively on this graph. So this is just a basic bit of permutation group theory. Now, some remarks. First, so if gamma is a two homogeneous graph, then its automorphism group is transitive of rank at most 3. And the reason for that is if you're two homogeneous, you can take any adjacent pair to any other adjacent pair. You can take any non-adjacent pair to any other non-adjacent pair. So the only possible orbitals are all adjacent pairs, all non-adjacent pairs. Maybe one of those is empty, but certainly ranks at most 3. And just a technical observation, the size of the automorphism group is even. Because if you give me any, well, assuming it's not the graph with one vertex. If I have 2 vertices, then there must be some automorphism that swaps them. So the group is even order. So, conversely, so G is some transitive subgroup of a symmetric group with rank 3. And if the order of G is even, it doesn't have to be, but it usually is. The order of G is even, then the all orbitals are self-paired. The fact that G has even order ensures we have at least one self-paired orbital, but if one is, the other one better be, because there's only 2 non-trivial ones. So self-paired means if you're not self-paired, there must be a pair somewhere. What you get from swapping the order. So the orbiters are self-paired, and so the graphs are corresponding graphs. Are homogeneous because well, again, you're saying just by the definition of the graph that one of those orbitals will have to be adjacency and one will have to be non-adjacency. and so completely homogeneous. And in fact, the two graphs are complements of each other. So it's a very, very nice situation to be in. And even better, final observation is that the G is transitive. If it happens to be in primitive, then has to be M, right, N, or the complete multi-vector graph. Because, well, if you have a G invariant equivalence relation, take all the pairs of distinct elements, they must be a union of orbitals. They can't be everything, so they must be either of adjacency or non-adjacency. And so actually you just get, so if being related means being adjacent, then you get this graph, and if being related means not being adjacent, then you get this graph. And so, as a theorem, due to many people, including at least one in this room, that the primitive rank 3 groups have been classified, and so as a cheeky corollary, I challenge you to actually go and work with them. The two homogeneous graphs are known. There's quite a few of them, depending on how you count your families. The way I do it, I think there are about 20 infinite families, each of which comes with a complement, and then about 60 exceptional examples, each of which comes with a complement. It's quite a lot of graphs. Okay, so, and there's one-dimensional outline groups, and we can have conversations about whether they've actually been classified or not. Anyway. So the last thing I want to consider, last possibility, something completely different, is the class of trees. These are connected acyclic graphs. And why do I care about the trees? Well, actually, when I was thinking about these things, I started to think about similar notions for instance functions other than graphs, which led me right back to graphs and trees. So I decided to stick with graphs today and talk about trees in the time that is left. Now, we already know something. Oh, actually, what's the name before I put this up? So let's call this, so I usually call this tree homogeneity, or TH for short. So actually back, it's long gone. Oh no, it isn't long gone. You can't read it because of the sun, but Gardner, back when he was thinking about CH graphs, he was already very unhappy with his choice of X, and he thought he should be able to do much, much better. And he did do better. And so something you can deduce from what he did is that if you have a tree homogeneous graph with girth at least 4, so no triangles, then it's connected homogeneous. I mean, of course, connected homogeneous implies tree homogeneous, but for graphs with girth at least 4, they're the same thing. And the reason for this sort of basic idea, and actually the idea how a lot of these proofs work, like how to classify homogeneous graphs or KCH graphs or CH graphs. Sort of basic idea is that if a graph is CH, say, then that implies that the graph is locally homogeneous. when you go down to the local graph. This isn't hard to prove. And so this gives you a kind of inductive approach to the problem. And if you happen to have a graph with girth at least 4, that means the local graph is just a graph of no edges. And so you can carry on exactly as you were. But if you have girth 3, then this is useless. And indeed, this is not true for girth 3 graphs. So let's start it with that. Basically, the issue is you might not even be locally arc transitive. And I'm going to show you an example where you're not. Very nice example, very well known. Just take the triangular graph. D of n. So the vertices are the pairs sitting inside of the set on up to n, and edges are things of the form ij and ik, say, or ijk are all different, so not empty intersection. The first thing about this graph is that the only induced subtrees are paths. Why is that? When you think about it, 1, 2 is adjacent to 1, 3. And something's adjacent to 1, 2, but not 1, 3. Will have to have the form 2, 4. So it can't have a 1, or else it would be adjacent to 1, 3. And if I were going to have another one, well, it has to have a 1 or a 2 in it to be adjacent to 1, 2. But if it has a 1 or a 2 in it, then it's adjacent to one of these. Right, so there's no way I can get a tree, an induced tree that has some vertex of degree at least 3. And once you've noticed this, it's just an easy exercise to prove that the graph is tree homogeneous. Paths all have exactly the kind of structure you'd expect looking at the definition of the graph. And moreover, it's not C3 homogeneous. I love this. The triangular graph is not triangle homogeneous. Brilliant. But why is that? If I take 1, 2, I get a triangle with 1, 3, and 1, 4. But I can also, I should say, this is for n at least 5. I can also take 1, 2, and 1, 3, and 2, 3. The automorphism group of this thing for n at least 5 is a symmetric group, but it's natural action on pairs. There's no way I can take the first one to the second one. Right, so it's not locally arc transitive, is what that says. I think I can finally erase my big table. Okay, so we have an infinite family of examples. Our old method is useless. How do we go about it? Well, very basic idea is to use paths. So if you suppose that you have a graph with diameter at least 3, so you've got some vertex, vertices at distance 1, 2, and 3. So that means I at least have an induced graph isomorphic to the path with 4 vertices. 1, 2, 3, 4. If I happen to have some edge here, which is not adjacent to something up there, then that's another P4. So I can go 1, 2, 3, 4. So I would have to be able to fix these 3 guys and that one to that one, but I can't. Because of course this one is distance 3, but this vertex and this one is distance 2. So that's this is basically what fails a lot of the time. In fact, get the following error, which I have just escaped. remember from what the basic properties said before, there's no loss in assuming it's connected, so it's connected. So, leave notation. So a path pk, this will denote the path with k vertices. And k13 is just the claw. And I'm going to take a p1 up to pd plus 3 k13 homogeneous graph. I'll tell you what d is in a minute. With curve free. Remember, we only care about curve free because Gardner already tells us what happens in general. Curve free, diameter d. Then, kind of using this idea as much as possible, you can prove that the diameter is 2. So actually, this doesn't happen. And in particular, this means that my graph gamma is 2 homogeneous. I've just spent 10 minutes talking about. Why is that? If you take 2 non-adjacent vertices, now that the graph is diameter 2, they must have a common neighbor, and that graph will induce a P3, which is in my list. So it's 2 homogeneous, so that means I know that my tree, well, in fact, my X-homogeneous graph for this mess will lie somewhere on the list of 2 homogeneous graphs. Okay, so I've been working on this for what feels like forever. But while I've been at the INI, I think I've finished it off on a complete list. So, in fact, so I've already made a mistake between yesterday and today in writing it down, so use this with caution. So gamma is one of, well, of course it can be connected to homogeneous. We've already seen that. Triangular graph is an example. We can take the direct product of 2 complete graphs, which is the complement of the CH graph I just erased, but no matter. You get the complement of an affine polar graph over field with size 2. What's that? The vertices are just a vector space in dimension 2n over the field with 2 elements. You have some non-degenerate quadratic form of type epsilon, and you join 2 vertices when their difference is non-singular. That's hence the complement. Or the local graph of theta 2n. Too far. Or 14 exactional graphs. Yesterday I thought it was 13, but it's just because I miscounted. It's not because I made a mistake.
Yes, very can such a mistake.
So 14 plus or minus a few. So, thank you.
Good.
Any questions for Joanna?
Well, just a remark. It's very interesting. I mean, what happens? I mean, there's obviously an analogous question you could ask for groups. You know, you've got a group and you've got a subgroup, and you ask.
I think people have done this.
I was just wondering if anyone had thought had been interested in this.
I'm pretty sure someone has,
Yeah.
but off the top of my
Peter
head.
Neumann, among others.
Yeah.
Well, yes.
I mean, it's basically been considered for pretty much anything you could think of.
Well,
It's
I've
been
really think
considered
about
for post
groups.
sets. It's been sort of all sorts of. There's a whole theory to do of Resse where he builds a whole theory of infinite to do with infinite graphs, and I don't know very much about it, but the model theorists think about this kind of stuff all the time.
What about colour graphs? Intentional graphs, is there?
That's a good question. I'm not sure I've seen color graphs.
Because that's a colour graph is just a relational structure, right?
Yeah.
They love homogeneous relational structures, don't you, Peter?
Goldfand had a theorem about that back in the 70s.
Who's
Goldfand, the guy who the other name that went with Gardner's theorem. I don't remember what the conclusion was, but he had a theorem about that. Ask Bishop Kling, he'll probably know.
How big are the exceptionals? I mean, how big do they get?
Not very big. So in fact, actually, I mean, I think the biggest is probably, the biggest degree is the complement of the Higman-Simmons graph. So that's degree 100.
A degree is 100.
Yes.
So you mean the number of vertices?
The number
So
of
you mean the number of
vertices.
vertices?
Yeah, I mean the number of
Number of
vertices.
vertices.
Yeah.
Oh, the order.
Yeah, yeah.
77 is the degree.
Sorry?
77 is the degree.
Yes.
Degrees
The degree of the graph is not the
Yeah, yeah. I'm
degree.
sorry. I'm talking about the
Yeah.
degree of the permutation group.
The order.
But actually, there's a really nice little set of examples. If you take, so there's the exceptional isomorphism between PSB43, P omega 6 minus of 2, PSU42, and omega 5,3. Take that. That group has 5 primitive actions. They all happen to be rank 3, and they're all nice things like actions on singular vectors, non-singular vectors, whatnot. So they're all rank 3. So in each case, you get 2 graphs. If you take the graph with the bigger valency, it's always tree homogeneous, which I think is quite a nice thing. So that accounts for 5 of the 14.
Is there a reason why? What happens if you don't get quite as far as D plus 3? Where's the 3 coming from?
The 3 is coming from, you can start to do, the problem is that this kind of argument, it never tells you anything about what's going on down here. It only tells you about things that are happening one step up from if this were the diameter.
Right.
And so this allows you to do things like this, or even that. So this is D plus 1, and then there's D plus 2, and then there's D plus 3.
Oh, I see.
Any other questions for Joanna? Oh, please all join me in thanking her for her talk. And the other part of my duty is to remind you all that there's wine and cheese.
That's completely unnecessary.
Even